In this session, we will learn more details about shuffling, partitioning, and sorting. We will also see how to optimize the MapReduce program using combiner class. Before that, we need to keep one thing in mind. Input-output operations and data transfer across the network are the most expensive operations while processing the data. If you have used Amazon Web Services, you will know that Amazon charges for the input-output operations, and it also charges for the number of bytes transferred across the network. So you need to keep these operations as minimum as possible. Let's get back to the word count example. Here we saw that the map function in each map task generates word as the key and numerical 1 as the value. These key value records emitted by the map function are not directly returned to the disk. Instead, it is first returned to the memory buffer of the map task. By default, 100 MB of memory buffer is allocated for each map task. When 80% of the buffer is consumed, these records are spilled to the disk. Spilling is done by a separate background thread. As a separate background thread is spilling the records to the disk, map output is not blocked. Map will continue writing records to the buffer. But if the buffer is completely filled, then the map will block until the spill is complete. Before the data is spilled to the disk, it is first partitioned. Here two partitions are created. If you remember, we had set two reduce tasks in our MapReduce program. Hence, two partitions are created. Within each partition, the background thread sorts all the records by the key. All these partition and sorting activities are done inside the memory buffer. Only then it is returned to the disk. If you observe the output clearly, you will see that 6 records are returned to the disk by each map task. Earlier I had said that input-output operations and data transfer across the network are the most expensive operations. So can we optimize our program to write less records to the disk? Sure, we can. This is where combiner class comes into picture. Like we wrote our own mapper class and reducer class, we can also write our own combiner class. In the combiner function, we will write the logic so that less records are returned to the disk and less records are transferred across the network. So what can we do in our word count example? In the word count example, we can add all the values of the same key emitted by the map task. That is, instead of writing numerical 1 for each word, we can write the actual count of the word from each map task. This is nothing but our logic in the reducer function. So we can directly go ahead and use the reducer class as our combiner class. In this example, combiner class matches the reducer class. But it will not be always true. The logic in the reducer function and the logic in the combiner function may differ. We may have to write separate logic in the combiner function. It all depends on your logic and the problem that you are solving. Let's go ahead and use the combiner class and write the actual count of the word from each map task. You can clearly see that the records are combined. Now only 4 records are returned to the disk instead of 6 records from each map task. This is really a good performance gain. So combiner function is called after partition and sorting is done. Only after going through all these activities, the records are returned to the disk. Till now we saw how records are partitioned, how records are sorted, and how records are spilled from the memory to the disk, and how combiner class is applied so that less data is returned to the disk and less data is transferred across the network. If you recall the HDFS sessions, you will see that you cannot edit a file in HDFS. Once the file is returned to the disk, that's it, you cannot edit it at all. You have to create a new file to add more data to the cluster. So when 80% of the buffer is consumed, it is spilled to the disk and a spill file is created. Once again, when the memory buffer is consumed, it has to be spilled to the disk. The earlier file cannot be edited, so a new spill file has to be created. This will go on till the map task processes all the records in its input split. As a result, there will be several spill files on the disk. Every time before the records are spilled to the disk, it is partitioned, sorted, and the combiner function is run on all the records. Before the map task finishes, the spill files are merged together to create a single output file. By default, 10 files are merged together at a time. While merging, it is again partitioned, sorted, and the combiner function is run. You can also compress the file and store it on the disk. This way, less data will be returned to the disk. So finally, we will have one output file from each map task. This file is stored on the data node where the map task is running. In fact, it is stored on the local file system. If you are using Linux, then it is stored in the Linux file system. It is not stored in the HDFS. This is a temporary file. It will be deleted after the job is completed. So we don't want to consume the space in HDFS. Hence it is not stored in HDFS. Instead it is stored in the local file system. Reduce task will start copying the records from the map output. Reduce task will not wait for all the map tasks to complete. As soon as one of the map tasks completes, reduce task will start copying the records. All the records in the same partition will go to the same reducer. By default, reduce task uses 5 threads to copy data in parallel from different map tasks. It copies the data to its memory buffer. When 80% of the buffer is consumed, then the records are spilled to the disk. Before spilling, it is merged and sorted. Again, the combiner function is run here so that less records are returned to the disk. As several spill files are created, a background thread in the reduce task merges the spill files into a larger sorted file. After all the map output is copied, the remaining spill files are merged together and passed to the reduce function. Let's summarize the contents of this session. Records are spilled from memory buffer to the disk. Records are partitioned. Each partition is sorted by the key. Sorting is done in the map phase as well as in the reduce phase. In the reduce phase, it is done before the reduce function is called. Reduce output is not sorted again. Combiner function is used in the map phase as well as in the reduce phase. In the map phase, it is used to decrease the number of input-output operations and to decrease the data transferred across the network. In the reduce phase, it is used to decrease the number of input-output operations. Before we end this session, let's run the word count program with the combiner class and see the difference. In this example, you need to set only the combiner class with the reducer class. Otherwise, you have to write a separate combiner class and set that combiner class using the setCombiner class API. I have already run the program. Let's compare the job statistics. First console window shows the statistics of the program without combiner class. Second console window shows the statistics with the combiner class. Here spilled records are around 119 million. Here spilled records are around 975,000. Here reduce input records are around 39 million. Here reduce input records are around 44,000. Here reduce shuffle bytes are around 24 million. Here reduce shuffle bytes are around 50,000. So clearly we have optimized our MapReduce program. It is always recommended to use combiner class whenever possible. That was all about this session. Thank you for listening to this session.